Hey guys, in this video we are going to be talking about steady state as chemical engineers or chemists or people studying thermodynamics would approach this subject. And the very best analogy to begin to introduce this subject is a bathtub. And for the sake of illustrative purposes in this video, I have a little planter's pot with an opening right here, as well as little holes at the bottom of it. And so what to think about when we say a system is at steady state is that we can say, and this is the technical version, that all the state variables have no time derivative. The time derivative of your temperature or your mass must equal zero, or your energy within this system. And so thinking about filling up a bathtub with water, if I was pouring in water into the top of this thing at a flow rate of, let's say, 5 milliliters per second, if my system is at steady state, then I will know that I have 5 milliliters of water exiting my system in the outlet stream. And I can also say, because we know that our system is at steady state, the time component of, let's say, the volume of water within this thing must also equal zero. So height as a function of time is just going to be a flat line at some number. It's a constant. So if you take the first derivative with respect to time of your height function, you know it's going to be zero. And this helps us simplify a lot of our material balance equations that are going on. And so, once you understand what is steady state, it we can begin to add more nuances to it. But before we do that, it's very important to make a note here that steady state and equilibrium are not the same thing, even though they sound vaguely similar. Um, in the case of equilibrium, what we know about equilibrium is that it tells us that the rate forward equals the rate reversed. And what that means essentially is that as a whole, there's no reaction occurring in our system. And so when you're a chemical engineer and you're designing a process and you invest significant resources into creating conditions within your reactor to induce some process, such as changing water into hydrogen and oxygen gas for downstream processes, you are deliberately creating an environment that is not favorable for water to continue to exist in its current state. You want the water to change into oxygen and hydrogen. And so reaching equilibrium means that you're not changing anything. You're taking water in and then you're leaving it as water. And so as a net, you're not doing anything, and you shouldn't even have a reactor in the first place because it's just a waste of money and resources at that point. So in the case of steady state, making our little example bathtub here more of an interesting example, what we're going to have in this case is we're going to have a flow rate of liquid water coming to the top of this thing. We're going to have some unreacted water coming out of this, because none of our reactions are ever going to go to 100% completion, which is what we should learn from chemistry. But we will have some products, and we're going to get some hydrogen gas as well as some oxygen gas from our system. And so when I tell you that I have a chemical reactor in my hand right now, and I have my liquid water coming in, and I have my products coming out, if I tell you it's a steady state, then that tells you that the time component of the liquid water coming out of my system, the mass flow rate of oxygen gas and hydrogen gas, are all constants over time. And inside my reactor, it also tells me that the pressure inside my reactor must be constant, the volume must be constant, and the mass, or let's just say the height of the liquid water and the mass of the hydrogen and the oxygen gas inside my little control volume are constant. And the other very important thing to do when you're learning about steady state is figuring out what is your control volume, because oftentimes that is your biggest challenge. And if you can figure out what is the smart control volume to draw of your system, it will save you a lot of time and make your math significantly easier later on. And so in the case of a little planter pot like this, my control volume is strictly the pot itself. I do not care at all about the flow rate of water that's coming in, or whatever else is downstream or upstream of my process. All I care about, for the sake of my material balance equations and my steady state approximation of my system, is my little control volume that I have very strictly defined to just be everything that is inside of this system, inside of this little pot in my hand. Okay? And when I first learned this stuff as a undergrad chemical engineer, I didn't fully appreciate the significance of this in terms of like living systems, because I did a concentration in biotechnology, and I am very much a fan of biotech and all that biology stuff. So when you think about cells and you think about intuitively what we humans want, which is calmness and equilibrium, um, when you reach equilibrium, you are dead because your cells are no longer doing anything. And what that means is we as humans and as living organisms, our cells are essentially just like a lot of the chemical reactors that we design as chemical engineers, in that they are operating at a steady state. Your cell is just this little bioreactor that takes in some feed, such as glucose and oxygen and water, and then it outputs carbon dioxide, ATP, and whatever else life wants to make, like some amino acids or something. But it is acting and operating at steady state because you have, in general, you do not have an accumulation of something. And when you have an accumulation of something, that's when we have some issues. So without getting too deep into the woods with the uh, physiology and all that other stuff behind this, just thinking about this very simply as your steady state hypothesis or assumption just tells you that the accumulation of everything inside of your system, there is none. You don't have to worry about it. There's no uh, accumulation term within any of your material balances where you have accumulation equals in minus out plus generation minus consumption. When you have steady state, you can say that your accumulation equals 0, which is equal to your rate in minus your rate out plus generation minus consumption. So all those four terms on the other side of your equation, they must somehow sum to 0, which makes your math a lot easier when you're solving these kinds of problems, such as figuring out what is the concentration of a particular species within your reactor. And so it also applies to energy. So the temperature in my system must remain constant. And when you get deeper into thermodynamics and learning about these things, it takes on a lot more meaning. And so I hope that you guys find this useful and interesting. Let me know if you have any questions, and thank you for watching.